In this set of notes, we're going to look at functions with two or more independent variables, and this corresponds with section 10.1 of the textbook. So far in the course, we've been looking at functions that look something like this. So we'll have an f of x is equal to, and then on the right-hand side of the equation, we'll have some function of x. So for example, we could have x squared minus 3x plus 2. And so in this case, we've called x the independent variable, and then if we set this equal to y, we would call y the dependent variable. But notice what we're really doing is we're taking a single number, x, and we are mapping it in accordance with this function and calling that y. And so here we have the formal definition of a function, and that's essentially what this formal definition is saying. It's saying that a function f is a rule that assigns each element x in the set A, and so usually the set A we've worked with is the real numbers, to exactly one element in y. And we could call this the set B, and typically B is also the real numbers. We've been mapping the real numbers to the real numbers. But we've looked at other examples. So for example, we've looked at examples where x was restricted to be greater than or equal to 0, and so on. And so that element y is called the image or the value of x under f, and is denoted by f of x. And set A is often called the domain of x, or domain of f, and B is called the codomain, or sometimes we will call that set the range. And so we can think of the domain as being the input to the function, and the range as being the output of the function. We can also have functions where the domain consists of pairs or n tuples of real numbers, and then they still map to a single number. So when we look at examples like this, what we say is that f maps the domain to the real numbers. And this notation is very similar to what we have up above. But before we get lost in the notation, I think it's easier just to see an example or a couple examples of what functions like this look like. And so notice here we have f of x and y. So notice this function isn't just going to take x as an input, it's also going to take y as an input. And then the output here is going to be 2x plus 3y. So in cases like this, we typically wouldn't say that function is equal to y. We'll typically pick a different letter. So for example, z. And so let's see what evaluating this function would look like. So for example, we might want to evaluate this at the point 1, 2. So in other words, we have f of 1, 2. And so everywhere that we see an x, we're going to plug in a 1. And everywhere that we see a y, we're going to plug in a 2. And so notice in this case, we would have 2 plus 6 is equal to 8. Instead of f of 1, 2, we could look at f of 2, 1. And so this time we're going to plug in x is equal to 2 and y is equal to 1. So in this case we would have 2 times 2 plus 3 times 1. So notice that the ordering inside of the function does matter. And this is why it's important when we write the function name like this, we also include the x and the y so we know what order we're going to be replacing those numbers with. Right, and then just as one more example, we could evaluate this function at 102 and 3, and that would be equal to 2 times 102 plus 3 times 3, which is equal to 204 plus 9, which is equal to 303. Now we're not restricted to just mapping two numbers. We could also map 3. So for example, here we have f of x, y, and z is equal to 2x plus 3y all divided by z. So notice in this case, if we wanted to just give this function a single letter, we wouldn't want to use z because that's one of our independent variables. So in this case, maybe we would call this w. And so that's just a notational thing. But let's look at how we would evaluate this function. So if I wanted to evaluate at the point 1, 2, 100, everywhere that I see an x, I will plug in a 1. Everywhere that I see a y, I will plug in a 2. and everywhere that I see a z, I will plug in 100. And so notice this is going to be equal to 2 plus 6 divided by 100, or 8 divided by 100. Again, I could evaluate this function at 102, 3, and 2. Everywhere that I see an x, I'm going to plug in 102. Everywhere that I see a y, I'm going to plug in a 3. And everywhere that I see a z, I'm going to plug in a 2. And so notice this is going to be equal to 103 divided by 2. Usually when we get to functions that involve more than 3 independent variables, instead of using different letters like we have in the last 2 examples, what we'll do instead is we'll use subscripts, and it just makes it easier if we have a whole bunch of independent variables. So for example, in this function, I wanted to evaluate it at the point 1, 2, 100, and 1. Everywhere that I see an x1, I'm going to plug in a 1. Everywhere I see an x2, I'm going to plug in a 2. Everywhere I see an x3, I'm going to plug in 100. And everywhere I see an x4, I'm going to plug in a 1. And so this is going to become the following. And then we could evaluate that fraction, and that becomes negative 90 over 100. Very similar, we could evaluate this function at 102, 3, 2, and 100. And so again, everywhere that I see an x1, I'm going to plug in 102. Everywhere that I see an x2, I'm going to plug in a 3. Everywhere that I see an x3, I'm going to plug in a 2. And everywhere I see an x4, I'm going to plug in 100. And this is equal to 103 divided by 2. So you'll notice evaluating functions with more than one independent variable is very, very similar to what you have seen before. It's just now, instead of plugging in one number, we're going to have multiples. But the important thing is, for this particular type of function, notice that when we evaluate the function, even though we have multiple inputs in our domain, we only have one output for the range. Okay, we are going to look at examples here in one of the preceding note sets where our output is actually vector-based, so you have more than one number. But for right now, we're looking at our input is a set of numbers, but our output is still just a single number. Right, and let's just look at one more example here. So suppose here that our domain is the set of x and y, such that x squared plus y squared is less than or equal to 9. So some pairs that could be in our domain. Notice we could have the pair 1, 1, and that's because 1 squared plus 1 squared is less than or equal to 9. So that's a possible value in our domain. 1, 2, which would be 1 plus 4, that's less than or equal to 9. That pair could be in our domain. But for example, the point 10, 1 would not be, because 10 squared is 100, plus 1 squared is 101, and that's obviously not less than or equal to 9. So any pair of numbers such that the first one plus the second one squared, if that total value is less than or equal to 9, those pairs are all going to be in our domain. And then here is our actual function. And so the question is, what is the function's range? And so in order to find the function's range, we need to find the smallest and the largest value the function f of x and y can take. All right, so the first thing to notice is that the square root of 9 minus x squared minus y squared will be greater than or equal to 0. In other words, the smallest value it can take is 0. And the reason for that here is that we do have a square root symbol. And so since we're working with the square root, we're always going to be greater than or equal to 0. So second, notice that x squared plus y squared will always be greater than or equal to 0. And that's because no matter what numbers we place in for x or y, whether they be negative, positive, or 0, x squared will always be positive, y squared will always be positive or 0, and therefore that sum will always be greater than or equal to 0. So, notice the quantity we have inside of the square root is 9 minus x squared plus y squared. So, x squared plus y squared is always going to be greater than or equal to 0. But also notice from up top that because of our domain, x squared plus 9 squared must always be less than or equal to 9. So, using these two conditions, what this tells me is the largest, and I just realized I was forgetting some parentheses here. I want parentheses around these. Notice the largest this x squared plus y squared quantity can be is 9. So since the largest this piece right here can be is 9, and again that is from the domain, that means that the smallest the entire quantity can be is 0, because the largest x squared plus y squared can be is 9, so of course 9 minus 9 would be 0, and then 9 minus anything smaller than 9 is going to be greater than 0. So we know this quantity has to be less than or equal to, probably has to be greater than or equal to 0. So that gives us the smallest value, and we actually already knew this anyways from up above. And now the question is, well, what is the largest this value can be? Well, now we ask ourselves, what is the smallest x squared plus y squared can be? And we know the smallest x squared plus y squared can be is 0. So since that is the smallest value we could take away from 9, that means that this quantity must be less than or equal to 9. Now, we're actually interested in the square root of 9 minus x squared plus y squared. So, if we take the square root of each of these, this becomes the following. And notice that the piece in the middle of the inequality, that is our function. So we know that our function f of x and y is greater than or equal to 0 and less than or equal to 3. And so that gives us the range. All right, and then there is one more section. So in your book, there is a section in this chapter titled The Graph of a Function of Two Independent Variables. And your book looks at different ways to visualize functions of two independent variables. Read this section in your book, and then after reading that section, I'm going to include a video on Canvas as well, how to use GeoGebra to produce some three-dimensional plots. So you can actually create some of the plots from your book on your own, and I'll show you how we can look at those and get a good feel for what these functions look like. So I highly recommend just playing around with the software, and the reason for that is the more that you kind of work with these types of functions with two or more independent variables, and the software is going to look at how to draw plots with two independent variables, I should say that. You'll get a better intuition about what these look like, and that'll become really handy in 675. So again, after you read that section in your book, do go and play with that GeoGebra software.